Sheet number 6, exercise 2. So this exercise is to get a little bit of practice with differential operators on a two-sphere, in particular also the use of two forms on a two-dimensional sphere. So whenever, I already said it several times, but I will repeat that, whenever I have your exercise, there are things expressed in terms of words. So out of that, you need to extract all the mathematical information that you have. So you know that you have, we're talking about a two-sphere, therefore the dimension of your manifold is 2. The coordinates that we're going to use are spherical coordinates, because we are a two-sphere, therefore the two components of the coordinates are going to be theta and phi, the two angles. Then we're going to need the metric, and the metric, you know, for a two-sphere, we have seen this already several times, is diagonal, and the elements are, for the 1, 1 element is, so the theta element is 1, and for the phi element is the sinus to the power of 2 of theta. The other two, theta phi and phi theta components are equal to 0. The determinant is trivial to find it from this expression, that's just the sinus to the power of 2. And the inverse, again, is a diagonal matrix, that's trivial, so that's the inverse of the component. So 1 for 1 divided 1 is 1, and 1 divided the sinus of 2 is the inverse of the sinus to the power of 2. Simply as that. Then you need to apply the Hodge operator to various objects, to various one form. So what you need to do is to, first of all, recall the definition. So you get the definition that Matthias gave you, and that's the one that you need to use. You write it there, and you keep it in front of your eyes. And then you just apply it. So we have our Hodge operator of the theta. Okay, so this is the theta is the basis one form, so it is a one form. Therefore, we are applying the Hodge operator to a one form. Therefore, P in our expression that appears here, 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 and here is going to be 1. It is going to be 1 because it's a one form. Then here in the recipe, you see that we have other indices, other numbers that should appear, and we have an n, right? And that's the number of your dimensions, and that's a 2. So let's start to play once, and then we have, you see, we have these other indices, and the other basis, and what are we going to use? The x, E1 is going to be the theta. Okay, that's it. E1 is going to be 1, and P1 plus 1, since P is 1, is going to be 2. That's the only other available index. So that's why we're going to use that. So let's apply now. We apply the Hodge operator to our one form, and we use the definition. So we have the square root of the determinant square root of the sinus to the power of 2. That's sinus. Then, as I said, we have a 2 minus 1, because it's a two-dimensional space, and a one form. So 2 minus 1 factorial, which is 1 in the end. So in fact, you see, here we are going to have the sinus and the sinus that is here, and this factorial of 1 is a 1 that we don't see there. Then what we have? We have the Levi-Civita, and the only thing that you need to remember about the Levi-Civita is, because it's totally antisymmetric, you need to remember when it's plus and when it's plus 1 and when it's minus 1. Okay, so these are the only two values allowed, and it depends on how they are displaced here on in your indices. So we applied, right? So we are basically using this. We are referring to E index 1 is 1, therefore this is a 1. Here we have a 2 because it's the only other available one that we have that is non-zero. So it's a symmetry, but we have to keep the non-zero ones. And so only those that are different than this one, because otherwise we would have they would cancel out, so they don't contribute. And then we have our basis for the x that will follow here: 1 plus 1, 2. Nice. So what do we need to do? Well, we know the Levi-Civita symbols, and when it's symmetric, antisymmetric, whenever we have the lower indices. So what we do, we lower this one we lower this one, and what we get, and to do that, we need the metric, the inverse of the metric actually. Therefore, we are going to have G alpha 1, and then epsilon alpha 2, where we have the alpha and alpha repeated, so in theory we would have a summatory here. And then we have the x2 that, as we mentioned earlier, so whenever it's the component 2, it refers to phi, therefore that's going to be the basis, the phi. And the result is just that, because the inverse of the only index that is non-zero is the 1, 2 here, which gives you a 1. Therefore, here we have G, 1, 1, and the inverse of the component, the inverse of the component of the inverse is, in this case, 1. And you are left with this. Okay? So, again, very simple. This is a one form, because this is the basis of one form, therefore it's a one form itself. So keep in mind that P is going to be 1, that you're going to plug here. That is going to be considered here, 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 and here. Okay? Then you have an n-dimensional space, and you're going to plug it here. In this case is 2. Then you have the square root of the determinant that you know, and you just plug it into here, and you get your sinus. Then you have your Levi-Civita. So actually, first you start with the basis that is going to be, since we are working with the theta, so that's the first component. The one that follows here, that apply to the Levi-Civita, are the other components that are left. Okay? Therefore, in this case, is phi. That's why you have the dx2, because that's referred to the phi. Then what you need to do is to lower the index of the Levi-Civita using the inverse of the metric. And that's it. You have your final result. Then the exercise is sort of a repetition, because we are going to do the same, but this time for the phi. So we are going to apply the wedge operator to the phi, which again is a 1p form, is a one form. Therefore, p again is going to be equal to 1. But what's going to happen is that we're going to exchange theta for phi with respect to the previous exercise. So we find again this 2 minus 1 factorial, which is this one, because it's again a one form. We are going to have the square root of the modulus of the determinant, which is the sinus, as before, so this doesn't change, you see. Then we are going to have, this time, we're not going to consider the x, which is let's say the opposite of what is left from the basis that we are using as an input. And in this case, since we are the input is the phi, here we have to use the other variable basis, and therefore is the x1, which is the phi. Here again, we lower the index of our Levi-Civita coefficient, but we have G22, because the only non-zero term that we have along the diagonal with a fixed 2, and that's sinus to the power of minus 2. Okay, this one. And it pops up here. In the end, you have this sinus to the power of minus 2, which cancel out partially, and you have your final result with the minus, which is coming from your lovely Levi-Civita symbol. Then we continue. We are going to have something a little bit more complicated. So you see that this is a 2 form, because we have two bases combined with an exterior operator. So you understand that this is just the basis of a P form, of a 2 form. Therefore, it is a 2 form itself. Again, we apply to it our wedge operator, Hodge operator, and we do exactly what we did before. So this time P is equal to 2, because we have we are swallowing two input bases. The determinant, the square root of the determinant is the square root of the determinant as before, no surprise. The number of dimension is 2 as before, but P is equal to 2, therefore we have the factorial of 0, which is 1 by definition. The factorial of 0 is not 0, but is 1. Then we have the Levi-Civita symbol, and this is the only one that is available, which is epsilon 1, 2. Okay, those with the same indices are equal to 0. So the only which is available is 1 and 2. Where are the bases? none. You don't have any other bases here. These guys, there are none because we have a two-dimensional space and there are no bases left on this side. That's it. Okay? And therefore what we need to do, as before, so there are no bases, what we need to do, what we are left to do is to lower these indices. This time we need to lower two indices, and therefore we have we need to apply twice the inverse of the matrix. Let's give you some minus and a minus, but then it cancel out, and then this is going to be our final result. Okay, so we have a 1, here we have the cosinus to the power of minus 2, here we have our sinus of 2, and this is the final result. That's it.